We are ready to start with our 5G-ACIA web seminar of today. I think there might be some people joining, but no worries, we will have some housekeeping notes before we can start, or will start then with our two talks that we have prepared for you today. First welcome from me. My name is Lisa Unterberg. I'm with the Institute for Automation and Communication, and I'm also chair of 5G-ACIA's Working Group 5, which is called Industrial 5G in Practice. And in this working group, we are in charge of the 5G-ACIA Endorsed Testbeds. We monitor the testbeds, approve their applications. We also offer them a stage to talk about their results, which we have one example today. Today's web seminar will cover two of our endorsed testbeds, one on international interoperability and the second one on TSN in practice. A warm welcome, so from my side, from 5G-ACIA to you. Thanks for joining, thanks for your interest in our web seminar. Before we start with the two talks, here's the housekeeping information as announced. We have a dedicated Q&A window, which you should find in your Teams navigation field. Please feel free to ask questions there anytime. We will address as many questions as possible at the end of the web seminar, which means we will have first the two talks and then in the end a joint Q&A session. If any questions beyond that remain open, I would like to invite you to become a member to get your questions answered and access to much more information than we can share in a brief web seminar. And for this, you can refer to 5G-ACIA's website or get in touch with 5G-ACIA office. This web seminar, as you have noticed during joining, will be recorded, and the recorded version will be made available afterwards. By default, everyone is muted except for the speakers. That's why it's important that you use the chat or the Q&A window for your questions. And if you have technical problems, please reach out to the office via the named email address. The colleagues there will help you out to finally join our web seminar. So this is the brief overview, and without further ado, we will start with our first talk, which will be given by Gustavo. Gustavo, the floor is yours.
Hello, thank you, Lisa. Hello, everyone. Give me 1 second to share my screen. Can you please confirm that you see my slides in the presentation mode?
That works.
Okay, thank you. Okay, thank you, Lisa. My name is Gustavo Pedroso. I work at IFAC, and today I will present one of the test beds, which is called International Interoperability of Industrial 5G. Let's start with a brief overview. Our joint motivation for this test bed, it's the interoperability and performance testing of 5G campus networks, private networks in Germany and in Japan. We also incorporate the use of SRF. I will explain about the smart resource flow technology in the coming slides. Yeah, as I said, we have two partners in Germany, IFAC and Denmark, and one partner in Japan, which is NICT. And the main motivation for us for this test bed was, okay, let's do some experiments in Japan and some experiments in Germany with components developed here and developed there, and see what are the learnings we can get from this. Some initial thoughts about interoperability. So yeah, the idea and what we achieve at the end were shared learnings, and not only measurement results, but also non-technical informations. I will explain a bit about it. First, I would like to briefly mention the 3 locations of the test beds. 2 were in Japan, in the Yokosuka Research Park in Yokosuka. and also in Sendai, in Tehuko University Labs. And in Germany, it was in Demag's research factory in Wetter. Something interesting from the setups or from the test beds, of course, they have many differences, but one of the main ones is the spectrum. The spectrum allocated in Japan is 4.8 to 4.9, while in Germany, as some of you know, is 3.7 to 3.8. IFAC in the test bed, our main activity or our main role was in the performance testing of the 5G systems here in Germany and in Japan. And for that, I would like to introduce our measurement system quickly that we call FTT. The FTT means Funk Transfer Tester. And here you see a 5G network, very simplified with the 5G core network as this cloud base station and a 5G device. And our equipment that you see here in this figure, it's composed of hardware and software. And the idea is that we have a traffic generator and measurement device. So we emulate the application in terms of data traffic, and we transfer data from a source to a target using our equipment. So we don't need to have a real application to assess the behavior of the network, but we can emulate the traffic and we can configure the traffic in different ways. And here we are representing like the testing for uplink and the testing the downlink direction. So we evaluate each one of the links. Something very important for our tests is the reference interface. That is, these points here is the points where we do the measurements. I will quickly talk here about the transmission time. The transmission time is the main parameter I will present today that we evaluate. And if you see here, the two parts of the source and the target and the reference interface, and we have a transfer interval where the application is sending data, and the transmission time is the time when the message was sent till it was received. For wired networks, this is mostly deterministic. For wireless, it's not always the case. There is some variety in transmission time, which is, again, here I would like to highlight the reference interface. Some key practical observations, something very interesting that we learned right in the beginning of the tests in Germany with the Japanese devices was something that the APN we had configured in the German 5G network had an underscore, and this was not supported by the Japanese device. This seems a very simple problem, but it's something that you just see when you are there commissioning the components, commissioning the devices. It was quite easy to adapt this. We adapt the APN format and then the devices could connect successfully. This is something interesting from one of the learnings we had in the experiments that I would like to bring today, because it shows that even small things sometimes cannot be foreseen. On the other hand, when we went to Japan and took some devices, we learned that due to Japanese regulation, the devices needs to be certified. The radio frequency devices, they need to be certified to be used. So we couldn't use some of our devices because the process would take too much time. And the solution was to move the network and to do experiments in the anechoic chambers. This is also very interesting because it's a problem that we got even before the testing, so it's something that really needs to be observed. Now, some performance testings. Here I show the network in Yokosuka. You see the network inside of the anechoic chamber, as I mentioned. And we use our FTT for perform the measurements. We run experiments in the uplink and downlink direction. And I would like to show here some transmission time results. This is This histogram shows the transmission time and the number of messages here, the vertical axis, and the transmission time is in milliseconds. So TE 23 milliseconds means that we send, so the FTT sends one message every 23 milliseconds, so periodically, and we measure how much time it took. So we are here below 20 milliseconds for almost all occurrences. For uplink, it's a bit higher. This is common in 5G systems that are not balanced in the number of time slots for downlink and uplink. So this is one selected result for many that we have performed. Here you see a table comparing different test cases. I showed before one with 23 milliseconds. Now we have results for 53, 11, and also from one UE to another UE. You see here the number of transmitted messages, 20,000 per test, number of received messages, and number of late cycle messages. This means that all the messages arrived, but some messages arrived too late. What's the meaning of that? If I send one message every 11 milliseconds, the system can deliver all of them, but not all in time. Some messages arrive late. This is important, this assessment, because, as I wrote here, many messages arrive late with 11 milliseconds, and this may cause errors or problems for field bus systems, like, for example, Profinet. So in this comparison here, we see that for Profinet, it would be, or this 5G system would manage a Profinet system that is configured to transfer data with 23 milliseconds or more. Yeah, so this is one very important hint or insight that we get from performance testing, how to configure or what the 5G system can do and what are the requirements it can handle. Here, a short comparison between the measurements. We did performance testing in Japan, as I said, also in Germany. You see here the results again for 23 milliseconds for uplink, for downlink in this case, and for uplink. For these tests, the network in Germany had better performance, even if it's just small differences, but the values are more concentrated in the low part of the chart. This is for many reasons, network configuration, distance between device and base station, and some other aspects. But we see that the results are quite similar. I would like to give some information also about the performance testing of 5G and Wi-Fi controlled by SRF. What I mean here? The Japanese partners, they developed a protocol called Smart Resource Flow, which is a platform that manages wireless communication systems, and it dynamically can choose a communication path if the device has more paths to transfer. For example, here we have an application connected to the SRF device, and the SRF device is connected over a 5G campus network, and it can transfer data over this network. But the SRF device can also connect to a public 5G network and also to a Wi-Fi network, to a VLAN network. So we wanted to explore how this system manages the communication when there are multiple steps to transfer. What we did a test in environment, a laboratory environment, where we had, as the application, we use our FTT, transferring data, periodically data, and over the SRF system. For this case, there was no public 5G connection. It was only a campus network that was installed in this room and a 5G, a Wi-Fi network. So the SRF could decide between 5G or Wi-Fi. And I would like to show one of the results we had for this case. Yeah, but first of all, I wanted to explain which kind of data we transfer. We configured our FTT to transfer Profinet RT-like data. What does it mean? We transferred layer 2 frames with the same fields that a Profinet RT message has, which means the SRF device had to transfer the data from the SRF device side to the gateway side, and the 5G network and the Wi-Fi network, they have to handle this data. And as we saw before in the performance testing measurements, the transmission time is very important and the determinism is also very important. So I want to show now a small result that we have when during operation, during the test, the SRF switched between Wi-Fi and between 5G. Yeah, so we tested in both directions. I will show in the downlink only. And what is important, the transmission time is very important for control applications in industry, but also, I mean, for the application perspective, the transmission time is very, very important. But from the protocol perspective, like for Profinet, in the protocol point of view, the regular update time, so that the determinism is more important or more critical. What does it mean? Of course, the transmission time is important, but it's important that the time between received messages keeps constant, so the Profinet device or the Profinet I/O keeps connected to the PLC. We didn't have here a PLC and a Profinet I/O, but we had our FTT emulating that, and we can then, in the results, analyze how Profinet would behave in this configuration. Yeah, this is what I want to show in this figure here. We have the results for the downlink. And here you can see the transmission time in the vertical axis. Okay, this is a scatter diagram. And in the horizontal axis, we see the message sequence number. So we have around 50,000 messages. And we send data, Profinet packets every 32 milliseconds. 32 milliseconds is a common configuration for Profinet. And we have a handover that is Wi-Fi, 5G, Wi-Fi. What does it mean? This first part here of the chart, it was data being transferred over Wi-Fi. Then SRF switches to 5G. We have this part in the middle, and then back to Wi-Fi. And this is interesting because while we see that, or the chart gives some impression that for Wi-Fi, the values are concentrated in a smaller value than for 5G. 5G is much more consistent. What does it mean? The values are higher, the maximum value or the average value is higher for 5G, but it's much more predictable. This is a very interesting result because, yeah, we cannot only think about average of the results or mean values, but we need to see how the system behaves over time. And this is something very important to be assessed before we install applications or even before we install communication field bus protocols on wireless communication networks. Yes, and to conclude, to quickly conclude, sorry. We did some cross-testing in Germany and Japan, and this provided us very important insights, into interoperability aspects, but not only, okay, if the device connects or not, or how the interoperability really works, but these small things, like, okay, the underscore that is very interesting. It's very simple, but very interesting. Also the case of the regulations, all these things that must be observed even before we install devices. With these tests, we could assess networks in Germany and Japan and see some small differences. And also we had the chance to combine 5G with other technologies like Wi-Fi and see how both would work together. Yeah, so these joint international tests reveal hidden technical details and some regulatory stuff, as I mentioned, which would be very difficult to know and to learn without this international cooperation. Yeah. So then to conclude, behind the testbed team, there is, so we are 3 members, but there is a group of supporters. And I would like to show this slide with all the supporters of this testbed. Yeah, thank you very much. And I would be happy to hear some questions later on. Thank you.
Thank you very much, Gustavo. There's some virtual applause for you.
Thank you.
We will answer questions after both talks, which is why I would like to invite the second speaker to share his screen. And while that's loading, please be reminded you can ask questions anytime via the chat or even better via the Q&A, and we will address them after Wahab's talk. Wahab, welcome. The stage is yours.
Good afternoon, everyone, and thank you, Lisa. I am Wahab, Team Lead Connectivity from Advanced Manufacturing Research Center in UK. I mainly work on wireless connectivity and cybersecurity for manufacturing sector. So topic of today's presentation will be, I will be presenting on progress and result of 5G end-to-end system for TSN communication testbed. So I will start off with the motivation. Manufacturing is being rapidly is changing rapidly due to digital transformation and automation. Modern factories rely on many connected systems such as robots, sensors, autonomous vehicles, and cloud platform that are continuously exchanging information. To coordinate these systems, factory requires reliable and real-time communication. Traditional wired TSN networks provide these deterministic communication, but they limit flexibility and mobility in dynamic factory environment. So that's where we are planning to extend TSN over 5G system. It becomes possible to combine deterministic communication with wireless connectivity. This will also help us to meet the strict SLA requirements of manufacturing, increase wireless flexibility, and will also eventually reduce the infrastructure cost. So at AMRC, we have one of the largest manufacturing testbed in the UK. These are 2 use cases which shows why TSN is critical for modern factories. On the left-hand side is a robotic cell. It requires tight time synchronization and sub-millisecond latency to control the robot movement in real time. On the right-hand side is an AI-based defect inspection system that pushes high-bandwidth video continuously on upstream. Both need reliability, but they need a very different network behavior. With wired TSN, network can handle this really well, but it keeps everything bolted onto the floor. Manufacturer wants mobility. They want robots that can move, tools that can be repositioned, inspection station that aren't tied to a cable tray. So that's where TSN features over 5G can help. So this testbed is a collaborative effort involving different industrial partners and research institutions. Each of them are contributing with different expertise. All of the partners bring unique capabilities on the table to bring this testbed in life. NXP is leading this testbed, and the physical testbed is located in Hamburg, in Germany. They contribute in hardware platform and play an important role in enabling TSN functionality and integration of 5G system. Then we have Belden and Moxa. They provide industrial-wide TSN equipment. We also have IFAC, which focuses on testing and validation side. And then two industrial partners, Mitsubishi and Schneider. They contribute in manufacturing use cases and industrial requirements. We also have Redisys, which provide the 5G core. And then ourselves, MRC, we mainly focus on system integration, experimentation, and performance evaluation. Recently, we have bring AI Link into the consortium or into the testbed. They are providing their industrial UE, and they will soon be joining this testbed officially. So in terms of our current progress, we started this testbed in 2024, and within less than a year, we demonstrated the first live system at Hannover Messe in 2025. The demo was deployed across two booths in different exhibition hall. One was the 5G-ACIA booth, and second one is OPC-UA Foundation booth. Both booths were connected through the same network via a centralized core. Industrial devices at each booth were present, and that provides the connectivity as a 5G gateway, allowing them to communicate over the same network. This also allows us to demonstrate the real value of the 5G system, where we are demonstrating a remote operation, remote machine operation, where a crane in one booth can be controlled from the other booth over the 5G network. This is a multi-camera use case. The physical setup includes 3 cameras generating video streams with different priority level. These cameras connect to a TSN switch, and then the traffic is being forwarded to a 5G device, which then transmit the data wirelessly through the system and through the 5G system. On the other side, the network or the data is then received and processed by a video server, which is controlling these 3 cameras. This is an architecture diagram of the same use case. We have integrated 2 TSN features into the 5G system. One is time synchronization, and the second one is time-aware scheduling. Traffic from multiple cameras, these are Ethernet cameras, into the switch, passes through this device-side translators, and then into the UE system. And on the network side, we have this network side translator on the core, and all of this allows us to test whether 5G can preserve priority, timing, and deterministic feature end-to-end. This is more of a detailed diagram of how we have approached this whole solution. So in this implementation, it's the similar continuation of the previous couple of slides. So we have 2 islands, 2 TSN islands. Both of them are connected through a 5G network, while preserving these traffic priorities required for industrial application. To achieve this, we have used a VXLAN tunnel to carry Ethernet frame across the 5G system. In TSN network, traffic priority is defined using PCP, or you can call it priority code point fields in Ethernet frame. However, these 5G system or 5G network handle traffic using IP-based QoS mechanism. So to maintain this differentiation, we need to translate these priority. So if you look at the table at the bottom, it shows the configuration of 3 cameras, C1, C2, and C3. C1 being the first camera 1 has the highest priority, C2 with a medium priority, and then we have C3, which gets the best effort or whatever remaining on the network. So each camera is being assigned with a different VLAN ID, VXLAN identifier, along with specific PCP, DHCP, and PyQI value based on its priority level. So I will try to give an example of how the traffic flows. So the first part is we have done the time synchronization, and then once the camera start transmitting, a camera first send an Ethernet frame to the TSN switch, This switch adds a VLAN ID, time slotting, and TCP value. Then the switch, then this packet is being processed by DSTT, which maps the PCP value to DHCP and also encapsulate the frame into a VXLAN tunnel. Then we have these 3 VXLAN tunnels, which are for each camera. And then the packet will travel through the 5G network with the corresponding 5QI. So these 5QI values, we have set it on the core and also on the RAN. And then at the receiving end, we go to network side translator, which removes the VLAN encapsulation and just restore the original Ethernet frame before it delivers it to the other side. And then it goes straight to the TSN switch, and then it will be transmitted to the video server. So in terms of testing, we have conducted a lot of thorough testing. I'm going to show you a video if it runs. Yep. So this is the similar video of the previous things I was explaining. So we have 3 cameras. From left to the right side, we have the highest priority, medium priority, and then best effort. What you can see in this video is high priority. You don't have any black lines. Black lines indicate you have a packet loss. Medium priority shows there are some packet loss, but in best effort, you can clearly see a lot of packet loss is happening. What we want to ensure is whenever we are putting a critical application, it goes in high priority, and that will ensure that this equipment or any manufacturing process gets highest priority over standard processes. In terms of result, we are able to achieve latency of 7 millisecond. This is one way, and then jitter of 0.8 millisecond. Time synchronization accuracy was around 0.9 microsecond. We have a packet loss of around 30%. We are working on it to improve it at the moment, but it's mainly due to the slotting mechanism of these time-aware scheduling. Right. In terms of next steps, our main goal is to enable basic TSN features such as Ethernet PDU session should be enabled on core and UE side. That's what we are focusing on. Before that, we were working on this VXLAN approach because Ethernet PDU session was not available in off-the-shelf systems. Second point will be we will be keep improving and testing different types of UEs from the testbed partners. We will also be integrating different vendor solution and test the interoperability of 5G and TSN system. And then we will also be building manufacturing use cases. We will be identifying its requirement to test the developed solution. Right. Last slide. Our main aim is in next few months, we are planning to demonstrate 2 more use cases, which will be focusing on flexible and reliable manufacturing. A mobile counter machine as a first use case, which will send data to a centralized command and control center with a virtualized PLC over the network. And then we will try to allowing the operators to monitor and control the machine remotely while keeping the factory floor layout quite flexible, because every thing will be controlled from the command and control center and from that PLC rather than having intelligence on the machine itself. So the second use case is about food and drinks production line, where we will be focusing on if there is any PLC fails, we want to ensure a remote backup PLC can immediately take control, ensuring that the production line continue to be running without any interruption. Yep, thank you very much. Happy to answer any questions if you have any.
Thank you very much, Wahab. Here's your virtual applause.
Thank you.
Which leads us to our Q&A session. Currently, I didn't see any questions via the chat or via the Q&A field. So this is the chance for you to talk to our speakers, to talk to our experts about any question that you might have. Just to yeah, maybe fill some time while some of you are typing. Wahab, I would like to ask you a question.
Sure.
You have shown metrics for packet loss and time behavior. To what of the priorities did they refer? To best effort or to high priority even? Because
so we have used three different types of priority. One camera will get high priority, which ensure that camera or that application will get the highest priority. The second one is medium, and the third one is the low or best effort, whatever remaining in the network. That's how we want to give that data to or the bandwidth to the equipment. So are you asking about 5QI value or what exactly your question is?
The 30% packet loss, so they are for all three streams in total.
It was for end-to-end testing, yes, for each one of them, mostly in the medium priority and the low effort. That's where we have the most packet loss. In high priority, we had very minimum packet loss.
Okay. How many packets were lost in high priority? Do you have a value for that, Tend? Okay.
I think it was very, very minimal, very, very minimal.
Okay.
I don't remember the exact number, but yeah.
Thank you for clarifying. Now there's a question in the chat that is related to this. How has the packet prioritization been handled on the RAN side, especially on the over-the-air level? Do you have a file level statistic, for example, a bit loss?
Yeah. So
sorry.
On
BLER.
Yeah.
Block error
BLER,
rate.
yeah.
Block error rate. Yeah, not bit, of course.
Yep. So what we have done is, these off-the-shelf RAN equipment, they come with predefined 5QI value, which you can use. So we have used those 5QI values to test the equipment. And we set up the same 5QI values on the core side as well. Regarding the physical level statistics, it's very challenging to get those statistics from the RAN itself. But if you have an SDR, then you will be able to extract a lot of features. Anything what you want is basically you can extract that information.
Okay. I hope that answered the questions. Otherwise, please follow up. Now there's questions both in the chat and in the Q&A. I'm looking at the Q&A right now. Can you inform WAP who's currently developing TSN translators and which programming languages are used for that?
It's AMRC. We are mainly working on the translator side, but other partners are also contributing from their end.
And how are the DSTTs and the 5G UE integrated? And what about the network side and UPF?
So let me read the question. How are the DSTT and Yep. So we are using C++ as the programming language. That was the first question. Second one was how we have integrated it, and not sure what does it mean. So in what sense he's asking the question? Is it on the same hardware? That's what the question is, or is it about how we have configured both things to talk to each other?
Okay, let's see. Maybe the person can clarify a follow-up. And while being clarified in the chat, there is the question by Christopher. Hi, you mentioned you apply IP PDU sessions. How would the performance change once you switch the 5G system to Ethernet PDU?
Yes, it will definitely improve the performance. In a sense, VXLAN adds a little bit of header into the Ethernet frame. That will be removed, so that will improve the performance, but not we're not expecting a drastic improve in the performance. But yes, there will be a certain change in it.
Now I'm checking whether there is a clarification on the DSTT and NWTT. Okay, not yet. It's been 20 minutes, but there might be also questions for the first talk as well. TSN is a hot topic.
Yes, it is integrated into the same hardware. I think the question came back. He was asking how it's been integrated.
Yeah. Perfect. So there we have a clarification, and I hope an answered questions, an answered question. Well, maybe some more people are typing a question to Gustavo. You mentioned the SRF and that the SRF does handovers between different technologies or between a non-public and a public 5G system. Did you also analyze how fast the handover works or whether it works 100% of the time? How reliable is this handover procedure?
Yeah, in the tests we performed, the lower transfer interval was 11 milliseconds, as I showed in the table for this measurement campaign. So for 11 milliseconds, there was no packet loss, no message loss, even when the handover was happening, which means is much, or it's faster than this 11 milliseconds. We didn't go to the limit because even without the handover, if we go to 3 milliseconds, the bottleneck starts to become the devices, you know. So there was no point to go beyond that. But for the case of 11 milliseconds, there was a seamless handover.
Oh, that's really fast. Interesting. And
Yeah.
now there's also a question in the chat to you. What Wi-Fi standard was used during the testing with SRF?
It was Wi-Fi 5. It was not 6 yet.
That was an easy question, it seems. Then maybe a second question, and let's see if there's further questions from the audience. When all questions are answered, or when it's 5 p.m. here in CET time zone, we will close. So now's the chance still to get in touch to discuss with our speakers. Gustavo, you mentioned that you performed tests in Germany and Japan, but of course you didn't test lots of 5G systems or combinations of 5G systems with devices. Of course, that's restricted by mainly time resources, I would expect. The results that you have, to what extent do you think they are valid for most 5G systems that are commercially available?
That's a good question. For this test bed, you are right. We had some limitations of device types for testing, but we also have experience from other test beds and other activities where we tested many different 5G networks, mainly in Germany, of course. In Japan, we had a chance to test 2 different 5G networks and 3 or 4 device types. So I think it's really representative, you know, especially because the results we got in Japan, they are, let's say, quite similar to the results we get in Germany. So I think the results from this test bed is quite representative, based also on previous results and previous experience and also references.
Okay, that's interesting to see, because results are as well quite interesting. So there's been some questions in the chat, but I think Wahab answered them in the chat already.
Yep.
Okay, we're very well within our time frame, which maybe gives us the chance to add the opportunity for the two speakers to add a statement that you feel is important to our community that you did not get to say during your talks. Of course, this is a spontaneous question. What would be the key learning from your testbed so far that you would summarize for our community?
Yes,
Kind of
maybe
as closing words for today.
maybe I can start. Maybe I was the first. I think that something very important is that the community works together. What I mean with that, we have in the 5G-ACIA community end users, device manufacturers, network providers, research, testing, and so on. We need to work together to put the requirements of end users, the knowledge of the experts that develop devices and networks, the knowledge and experience of who is testing. Only in this case, only putting these things together, we will learn things as we learned today in the test, in the presentation about real practical issues, and we will manage to solve them and to see what really 5G can do for industry. I think that this is the main key learning or the main key thing for me.
Thank you. And Wahab, what for you?
I agree with Gustavo. His point is very relevant. Second thing I want to mention from our testbed perspective, I think the most important thing is you need to talk to people. You talk to people, discuss the requirements, avoid any assumptions if you are working on things, technical things. The more you talk, you understand their capabilities, and with capabilities, bring innovation and also collaboration. That is the main benefit of these testbeds.
Thank you. I think that's very interesting that you both select statements that emphasize the collaboration between people. That this is the basis to make industrial 5G happen in practice. There's one more question in the chat, but I think Wahab will get it in the chat. And in the meantime, I would move over to close today's session, because that was two very nice closing statements. I would like to thank you for taking your time, for discussing, for your interest in industrial 5G. If you want to stay tuned, you can follow 5G-ACIA on LinkedIn. Here you can also find a QR code for an easy access. I would also like to thank our two speakers, Gustavo and Wahab, for taking the time, for preparing, and also for discussing. I think it was very interesting to hear about two topics that are already relevant in practice or will become more relevant soon. And last but not least, I also want to thank the office for organizing the web seminar series. That concludes our web seminar for today. We're looking forward to keeping in touch. Feel free to reach out to 5G-ACIA office. And with that, thanks again. Have a nice day. Talk to you soon.
Thank you very much.
Thank you. Thank you very much. Bye-bye.